So, sorry we're starting a couple minutes late. Obviously the 15-minute break has kind of got us all off. So this is our certification program, hardware concerns, track C31. So our first speaker is Sven Bettendorf from TUV, and he's speaking on side channel vulnerabilities. So please go ahead.
So,
thank you.
Thank you. So welcome to this talk. Sorry for the short delay. I kind of messed up the timing, but nevertheless, I probably get a little bit time back. So yeah, my talk is about side channel resistance of the new algorithms. Firstly, I wanted to present the algorithms, but I think you already got a few presentations about the FIPS standard, so I probably skipped that. But nevertheless, I want to start to introduce TÜViT to all of you. TÜViT is an independent evaluation facility based in Germany. We are doing certification testing, evaluation testing, also validation in different areas. We're starting at the software level up to hardware level. We also do site audits. So everything that is needed for an evaluation we can do. We're mostly working in the common criteria area. So most of our work or our daily business is common criteria testing and evaluation. We also have a FIPS certification, so we can do FIPS measurements and validation and hand out certificates at the end. So two topics that are maybe interesting for you is the bottom one. So it's post-quantum security, where I'm responsible for. This includes the post-quantum cryptography, but also quantum key distribution or any topic regarding quantum technologies that is upcoming. And this is also very important. And at the end, I will give an outlook on what could happen in the future. I myself from the hardware evaluation part, so I'm normally doing laboratory working, testing, measuring chips, doing the side channel analysis. So this is why maybe the talk will be a little bit more technical, but I try to make it so easy that everybody can follow here. All right, just a little throwback about the standardization call. It was all started 2016. Back then there were roughly 70 submissions, so 70 different algorithms were handed in during the different rounds. A lot of them were broken, just based on a bad problem, and a lot of them were just disregarded because of their performance. All of them were rated in mostly three different components. So one is security, for sure, how secure is the algorithm. The second one, how large is it? So how large are the artifacts, the key sizes, the signature sizes? So everything there would be taken into account, and then see which algorithm performs the best, and also speed. So nobody wants to wait like 5 minutes before the algorithm is done encryption or decryption. So speed is obvious factor. All right, so now I want to introduce you side channel analysis. Everybody here talked a little bit about it, but I'm maybe give you guys a little picture so you better understand what side channels are. So side channels are separated in two different categories. One is a passive side channel, where you just observe what the chip is doing. Here at the picture you see a probe placed on the surface of an IC and just measuring the M radiation. We also measure the power consumption. And most famous are like timing attacks. In work from 20 years ago, timing attacks were the most threat. Meanwhile, AM radiation is the most threat to the new chips. Then you just need an oscilloscope where you measure the different things, so AM radiation and power, and then in the end you can do some statistical tests on the measurements and try to guess or try to find out what secrets were used during the computation. The other thing that is active attacks. Active attacks are mostly there to somehow fault the algorithm and introduce some faults that can lead to some advantages. Mostly it's laser pulses at our laboratory. This means it's the most precise one. It's not the cheapest one, but it's most precise. You can really bring faults or bit flips into the correct register at the correct operation, but also some other fault attacks are possible, like voltage bursts or M pulses. These are more older ones. The most up-to-date ones are laser pulses. All right, so maybe a quick overview I did before I arrived here. I just typed in side channel attacks on RS, RSA, and Crystal Kyber, just to get an overview how many publications were done in the last year. You kind of see that it started all back in the 2000s for RIS and RSA for the classical parts. And since then they arose, and there were every year new attacks published. And even in the latest years, so last year there were new attacks. Even this year, a few months ago, or beginning of this month, there were a new attack published. So there is still research ongoing. There will be new attacks found. And even in the Kyber ones, you see at the bottom, there are not many publications, right? So there are maybe 20 or 30 a year. That is nothing to the up to 1,000 of RIS and RSA. So we have a lot more to look at, and we have to see whether it will find out new attacks, new potential weakness of the algorithms. So I expect that this publication number will grow in the next years, and so maybe in 2 or 3 years they will be as high as the classical ones. Since we know that there's a lot of research needs to be done, we as TÜVE decided 2 years ago that we try to help and try to analyze the two algorithms. Back then it was Crystal Kyber and Crystal Lithium in the 3rd round submission. And now I'm going to present a little bit about what we did and go step by step how we attacked the ship and what was the weakness. All right, so first of all, here's the algorithm of the Crystal Kyber 3 submission on the left, and on the right side there's the FIB standard, how it's looking now. And we try to attack the message M. So if you have the message M, you can just calculate the SHA and get the shared secret. So the M is actually where what you need as an adversary. And we just looked at the algorithm pretty plain and simple and see where is M used. And M firstly is used at the decode function. The decode function is nothing more than transforming the message bitwise into the polynomial representation that is used in Kyber. So it already sounds, if you're a little bit in the field, like this is a potential where it can all go wrong. And in the new FIB standard, it's also the same or the similar algorithm. It's also going bitwise through the message M and decodes it in the polynomial coefficient view. There were two actual algorithms that were presented that can do these things. The first one is here, where it's with an AND operation and the mask. So if the bit of the message M is 1, you just AND and mask on there and put the Kyber Q half, that is the modulus half, as the polynomial coefficient, and if not, it's 0. And the second algorithm presented, it's kind of similar. It's just a multiplication with 0 or 1, but in the end, it does the same thing, right? Okay. So now we go to the results that we saw. Pretty simple. We implemented it on FPGA, just measured it, and this is only the power consumption. And we see some patterns in the trace. They are separated here by the lines. And this looks really drastic and bad because you can just read out the message bitwise. Everything that is red circled is regarding the message be at this position 0, and if it's a little bit lower, it's 1. So everybody just need an oscilloscope, measure the power, and you can just read out the message M bit by bit, and in the end you have the message M and you can calculate the pre-shared key and nobody would notice, right? So you can completely break the algorithm just by looking at power traces. Similar is this with the second algorithm, where it's the multiplication with 0 or 1. It's not this easy to see, but still you can just go bit by bit and get the message M out. All right, so what I wanted to talk here about it is that there are countermeasures from the classical part that you can just use or implement in the post-quantum cryptography part, right? So masking, randomization, everything that is known to work in the classical part can also probably work in the PQC part, but it always has a downside. So if you increase security, you probably have a downside, either speed or precise or whatever. Here we have different countermeasures, and you can see in the last row is the only one where we had no indication whether the bit is 0 or 1 anymore, so we had to guess. Random guessing is 50%. But the downside here is that these algorithms where it transformed the message M takes 2.5 the amount of clock cycles. And 2.5 is actually kind of big. And And this is the downside. So if the speed is going down, maybe there were another algorithm that was easier to protect for side channel analysis that has not this downside that you need to implement such a countermeasure. We don't know because most of the algorithms were not tested for side channel security. There was no time to test like 60 algorithms. For sure not, but I think that in the next circle maybe there will be some new algorithms which include a little bit of side channel protection or side channel measurement and then calculating overhead. The second thing I want to present is our measurements on crystal kyber, crystal lithium. It's a signing algorithm, and we actually took the same steps as before. So we just looked at the algorithm, what is the secret, where is it used, where is it touched. In this case, it's a secret key, and this is the result. So the secret key is used in 3 different occasions. One is the decoding, then there's the NTT transformation, which is used in every lattice-based cryptography, and then there is a multiplication coefficient-wise. And since we had the decoding in the Kyber algorithm and multiplication is known to be leaky from the classical part most of the time, here we looked at the NTT and we did another statistical analysis of the results. It's on the left. This is one with template building. So we first looked when we have this value, what will be used in the power line. So we recorded as a template and then we just measured one time, one trace and tried to match it to the template that we built before. And we had a success rate of nearly 100% through all classes. So we identify the bit even there completely correct. So both algorithms, if you implement them completely plain, are not secure against side channel attacks. Right. Okay, so I speed it a little bit up so we can be on time again. So my outlook here is that we are on the right track. So we are now in the stage where we need to play around with the algorithms. We need to find new ways to attack. We need new countermeasures. We need to implement them. We need to test them. We need to verify them. And this will be done in the next probably 5 years before we can really say that this is the implementation or these are countermeasures that work and this will be efficient. That's why we as TÜV IT propose, or even the BSE is saying this, that there should be a hybrid approach in the future or in the beginning, because we can never say that the PQC algorithms are as secure as the classical ones. And as long as there are no quantum computers exist, we could still rely on the classical security that we know of. Also, crypto agility is a point, because we are not sure if the algorithms stay secure. We saw it in Psych, that was broken in the last round of the NIST call. We saw it with Rainbow or GEMS, the signature algorithms. They are all broken at pretty much the end of the research that was done on them. So we are not sure if it stays secure or even new quantum computer, quantum AI can come and break algorithms. We are not sure what will happen in the future. There will be a lot of changes. So I think, or we think, that agility and hybrid processes should be mandatory and should be implemented at least for the next 5 to 10 years. Right. Also, I mentioned quantum AI is a big thing. There are paper out there that tell that even quantum AI can maybe even break IIS. It's just an open thinking paper from IBM, I think. We have to see what's coming next. We will never be sure that the algorithm we are now developing or using or implementing will stay there for the next 5 years. So I think there will be a lot of change, and if we now go to crypto agility, we can then just transfer the used algorithm to another one. Quite simple, and don't have this overwork that we have to do right now to just change hardware everywhere, change software everywhere right now. This is a lot of work. Also, we need more guidelines. The BSE has some IS 46 or 46, where they give best practices against or for implementation of RSA, ECC, which was redone last year by us also, the ECC guide at least. And this will be done in the future, hopefully for PQC and PQC algorithms. So there will be a guide what vendors need to look at when they implement these algorithms and what are possible attacks that needs to be covered. This is important during an evaluation, because right now no one is sure what we have to look at and what we have to measure. And there's always an open discussion between the evaluation body, the developer, and the certification body in the end. We may or may not oversee something, we will never know. But yeah, this is with such a guideline that will hopefully come up in the next years, we will be more sure. Also another topic that I mentioned before that maybe influence side channel analysis in the future is there's an ongoing project in Germany right now that calls for quantum sensors used for side channel analysis. Quantum sensoring is or can have advantages over normal probes. They can detect maybe some magnetic fields better or have some 3D solution of the ship in just a second or for the whole time. So maybe even this will influence side channel analysis in the future. So there maybe will be new probes, there maybe will be new attack path, or maybe something that we don't think of right now. So we need to stay on track and need to be on time and need to be able to adapt in the future, right? Okay, this was a little bit of time done. Thank you very much for your attention, and if you have any questions, feel free to come up to the mic or hit me up afterwards.
Are there any questions? I actually had one, amazingly enough, because I don't usually do any quantum. So are there any publications on recommendations at this point for how to implement, try and implement post-quantum in ways for recommendations to avoid side channel problems?
Yes, so but there are only 2 of them I know that cover the whole algorithms, but there are a lot of publications that cover parts of it, so we have to combine different publications, and also our paper that we published have the countermeasures on how we implement them published, yeah.
Cool. Any other questions? Okay.
There's one, yeah. I think.
You mentioned that we should try to break these algorithms in the next 5 years or earlier, but do you think Shor's algorithm still is useful to break these algorithms, or we have to invent new ways or new Shor's algorithm to break this?
So for the Kyber ones, we probably need new quantum algorithms, so Shor will not break the algorithms. I'm pretty sure they are secure to the state we are now of. So we don't know any attack that is possible, but there was a paper, I think last year, December, where they had this was faulty in the end, but they told here this problem maybe can be attacked by a quantum computer, and this was a similar problem to the Kyber problem, not directly. And this will come up in the next year. So there will be development in the quantum algorithm part. There will be new research done, what can be done with such a computer and with such algorithms. So I believe there will be some publications that infect the security of some algorithms, yeah.
Thank you.
Okay, I want to thank Sven for an interesting discussion, and thank you for getting us back on track time-wise. Thank you.
Thank you.
All right, so we'll get started with the second session here, session 31, C31B, hardware equivalency for single chip modules, with a presentation by Yann and Swapneela Unkule. And so I think we'll let them take it away so we can hear all of them. Thank you.
Thank you, Brian. Good morning, everyone. Thank you for attending this presentation. So it's going to be a joint presentation between Qualcomm and atsec. So I'm going to start discussing the perspective from a vendor, and then you will have the perspective from a CST laboratory. So this presentation is about hardware equivalency for a single chip cryptographic module. And I'm going to present the challenge that we are facing and how we can potentially address them. So I'm going to start, I think that the paper, thank you. So I'm going to give you a short presentation with Qualcomm. So it's a short ads, but it's more than that, and you are going to understand why. So Qualcomm, American Multinational Corporation, headquartered in San Diego, California. So we are specialized in semiconductor, software, and services related to wireless technology. And our business include onset, automotive, cloud computing, Internet of Things, consumer devices, and edge networking. So we have a very large panel of products. And preparing this presentation, I was surprised that myself that we offer more than 450 chipsets. And we are receiving many requests for FIPS 140-3 certification. And so we want to find a way to reduce the number of testing because it's very challenging to address that. So I'm going to transition to the next slide, which provides an overview of what we want to achieve. And so maybe the first thing is who is impacted by that. So it's mainly the vendor of chipset, the CST lab, the customers that we can have because we don't. We have. Many of our solutions is for customer. We don't have. We don't provide direct products. Federal Agency and CMVP, and it's about single chip, sub-chip cryptographic system, and also hybrid. The why is so chipset can be available in different versions, and performing the validation test for all this version again is very challenging, and also testing doesn't always provide any additional assurance about the security function and compliance as well. And so for the O, so we are going to propose an option to reduce the number of testing, and so that will be more detailed in the presentation of Sonia in the next slide. So going to the next slide, so maybe to give a naive, not naive, but a high-level overview of chipset. And so here it's the kind of the type of block diagrams that you can see for modern chipset, like the system on chip. So you have several subsystem components performing their own operations. And for example, from a cryptographic standpoint, the operation can be done in only one block. So typically the security block, so you can also have cryptography at the CPU level, you can have cryptography operation on other components. I'm thinking about wireless system. And something that I didn't mention is on the number of FIPS editions that we can have, you need to understand also that we perform FIPS certification at the subchip level. So if you have 6 components which need to go through the FIPS validation certification, you multiply this by the number of chipsets, so it's just a huge amount of FIPS certification. And so impact the vendors, but the CST lab as well, as the CMVP, because we are submitting even more reports to them. Still about chipsets, so generally, so we design by chipsets the bare die or the package, the package die, and into the package you can have other components. Regarding FIPS 140-3, and so Swapneela will detail that a bit longer after. We are so the cryptographic boundaries of the chipset of the the cryptographic boundary of the chipset is generally done at the single chip level or at the subchip level, and sometimes a multi-chip level because now we have solution with several dice in package. Still about chipset, and that was a question that we had, why claiming hardware equivalency when you have the same die. So you can have some chipset with different configuration or different package, even if the die is the same, and so this chipset are can be identified with different names. And so from a FIPS certification standpoint, that means different operating environment, even if the functionalities which are implementing the cryptographic algorithm are the same and physically the same. So yes, and so yeah, one point as well is so the chip. So the underneath components, the die. So if we have the same physical implementation and the configuration is the same, the functionalities are going to result the same. So you are not going to have any difference because it's the same implementation. I mean, it's immutable. Moving to the next one. So this is to introduce a bit the manufacturing process. So I will provide, again, high level. I'm going to skip some information. You have very good presentation online, very detailed. So I'm just going to provide the elements which allow understanding a bit where we want to go with this hardware equivalency claim. So during the development cycle of the chip, so we are going to have several teams involved, preparing. So we are going to have the preparation of the RTL design, preparation of the layout, placement, all other information, analog part, and so on. And all this information are going to be translated in files, files format information for the manufacturer for the manufacturer or the manufacturer teams to produce the integrated circuit, the die here, so regarding how this is done, so when all the development cycle are completed and we provide the solution, the recipe to the manufacturer, they produce what we call a photo mask, which is used in the lithography process. So lithography process is when you have, so you have a wafer. So here I provided a definition. So it's a piece of silicon on which you have some chemical recipe on it, and you have so light is applied on this silicon, and so we are producing on the same piece of silicon the same copy of the integrated circuit and copy on the integrated circuit. And so where I want to go here, it's so this so during the production, the photomask is used to repeat the pattern of the IC on the wafer, and that for several wafers, which is going to result in the die. So the die is a unique individual pattern of the wafer, and so you will not have any difference between the die which is at, let's say, at the top of the wafer and the one at the bottom, and for the next wafer in the production sequence. So even if these die are used in a different package or integrated with other components, the physical implementation of your integrated circuit, your die will be the same. So going to pass on the next one. And so what we propose here is to be able, in order to identify that the die are the same, is to use the photomask ID. So the photomask is not only one photomask. I didn't mention that in my previous slide, but it's a set of masks, because now with the modern chip you have several layers. So it's really an identification for the material for the manufacturer or the manufacturer team to produce the die. And so we would like to provide, we would like to be able to provide the photomask ID to demonstrate that the physical implementation of this of the dice are the same, and why is that? It's because we want to be able to test only one product, one chipset, and not to have to retest all the chipset, without having to provide the die identification, but the photo mask ID. One other point to better understand the configuration. So, like other operating environment, a physical implementation can be configured. So you have some mechanisms which allows having the physical implementation behaving differently. And so we understand why we have some time to replay testing on chipset which have different configuration at the physical implementation level. Now, I believe we can also provide evidence that even the configuration change that will not result, that will not have any impact on the security, but maybe that will be for the future. But so. Yeah, it's reasonable to think about retesting when you have a change in the configuration of the chipset. Now, when we have the same configuration of the single chip, or when you have a subchip and the configuration of your subchip physical implementation is exactly the same, we believe that testing only once will be sufficient, because if you perform the test on one chipset, you will have exactly the same result for the next one, including for the security functional mechanism. And so, yes, another point is from a chipset standpoint. So, as I mentioned at the beginning, we have several components, several subsystems, and so the subsystems are not interacting, are not interfering with each other. Meaning by that, you are not going to have a subsystem which is going to modify the configuration of your subchip, for example, or the parts that you are validating. You are going to have communication between the components, but you are not going to have a change. I mean, if you change the configuration of one component, let's say, I don't know, the Bluetooth component, that, and your scope for the validation is some security IP, that is not going to have any impact on your security IP in the sense that they are completely independent. So, having said that, this leads me to the takeaways. So I'm going to repeat. So yeah, testing the same physical implementation with the same configuration, or testing the same physical implementation, with the same configuration will provide always the same result. The numbers of FIPS 140 certification for single chip is just increasing at a high rate. So I can tell you, I'm well placed to speak about that. So we are going to have a number of certification which is going to increase, and so that will have again impact on us, impact on the lab, and impact on the CMVP, plus indirectly the customers and the federal agency, because they will have to wait to get their certificate. And so, yeah, I mean, it's obvious, but performing validation tests involve resource and fees. I can tell you that it takes time to be able to get the validation done. It's not, I mean, we have fees, we are fine with that, but if it's relevant to do the test. And we are, I mean, as a vendor, we are able to provide the evidence that we are using exactly the same, we are able to provide the evidence that the same dice are used. And mainly, the conclusion of that is we want to avoid unnecessary tests when it's possible. And so I'm going to handle it to Swapneela. Thank you. I will take the question at the end.
you, Yann. Okay. No, that's fine. I think the slides have to. Okay, thank you. So I think Yann explained the vendor side, specifically the manufacturing step, where we can see that if you use the same photo mask ID to generate, different dyes, they are just copies of the same dye. And at the end, if that dye ends in a monolithic IC, in chiplets, or in anywhere else, the functionality should be equivalent as long as the configurations are same and the photo mask ID is same. Now, how can we take this information and connect it to the FIPS? That's what we are going to see. So our goal is here to have the maximum possible reuse of the test evidence and doing a targeted retesting only for the differences between the module. Specifically, we'll look at the reuse of the algorithm certificate, the ESP certificate, and the functional testing reuse. This is going to be applicable for any module that has a hardware die as part of its module boundary. So it can be a hybrid module or it can be a hardware module. It's not for the module where the die only implements a subset of functionality. That means it's only doing a set of operation within instead of a whole algorithm, or it's implementing certain FIPS requirement but not in its entirety, because then you have the firmware or the ROM or other components come in, and then you cannot claim the direct equivalency based on the photo mask ID. And let's start with the certificate reuse. So here our job is made easier with the CAVP FAQ that specifically mentions that the vendor is not required to choose the package IC as the physical boundary for the ACVP, and you are allowed to perform validation on the die. So as long as you have the die listed on the certificate, anywhere it goes in any different packages, you can still be able to claim the certificate being reused. However, for commercial reasons, people or the actual chip manufacturer may not want to disclose this information about the photo mask ID or the die on the public website. So for them, there should be a way to have a traceability between the mapping of the die and the packages, which they can easily provide to the lab, and the lab can include that in the test report when giving it to CMVP, so that their information is still protected, but they can still get a reuse of the test evidence. So let's look at an example here. We have 3 different modules which are using the same exact die, and the die, let's say for simplicity, only implements AES algorithm in its entirety. Now you also have different components that are part of the module boundary, like ROM and firmware, but they are not part of the die. So in this case, using the CAVP FAQ guidance, if we get the AES algorithm certificate for OE1, it should be also reusable for OE2 and OE3, as long as we know that the die implements the AES entirely and the vendor can prove that the die has unchanged. And the way to prove it is through the photo mask ID. These details can be available from the vendor to the lab and then finally to the CMVP. The core part is it should be up to the vendor if they want to get a certificate directly at the die level, or they want to protect the information, put it the IC name, and the mapping can be done in the test report. Then let's look at the functional test reuse. Here I'm putting some requirements that are required for single chip or the sub-chip module. Specifically IG23B additional comment 3 specifies that if you have any change in the versioning of your single chip, whether it is outside of, even if it is outside of your sub-chip boundary, and even if it is security relevant or not, you are subject for revalidation. And the revalidation specifically goes back to the management manual section 719, which is the porting of a sub-chip. So they mention that when you port your module from one chip to another, you have to perform regression testing, which does involve, lot of testing. So the reason being given here is because you have to do the testing after fabrication, that is after converting HDL or gate information to physical circuitry. But the photolithography process, it's actually printing the photo mask. Using the photo mask, it's printing your design onto the circuitry. So it is essentially performing the step of converting your design into the physical chip. So this can be used to say that if you have a die that is being used for that module, at least the implementation within that die should be reusable on the new chip as long as you have a same photomask ID. And then there are also some other areas that we can see it on the next slide. Similarly, for a single chip module, consider that you have your boundary as an SoC. If you do any security relevant changes on your firmware, you are still subject to the full regression testing, even if some of the hardware component may not have changed. In this case, if you can claim some of the reuse within the die, because if your photomask ID did not change, you can at least save some of the testing instead of doing a full regression test. We do have in the management manual the operational equivalency testing for hardware modules, which is basically if you have differences in power supply, memory, all these things, you can claim the reuse based on analysis only or a subset of testing requirement. But the focus there is not on the components that implement the crypto, where we want to claim the similarity instead of looking at the differences just at the component level. And the computational devices are out of scope for that specific guidance. So let's look at an example here. Let's say you have three cases. One is you have a hardware die where your hardware die itself is your module boundary. In this case, if the vendor has different packages, ideally the only thing that's getting affected is the physical security. Everything else should be exactly same. Then the next section is if you have the same die but you have differences you have the same package but you have differences in the configuration, then as Yann mentioned, depending upon what the configuration changes are, you could actually qualify for a non-security relevant change, or you may not even have to do the change if the configurations are not affecting your specific die. The third part is if your hardware die is just a part of a module boundary, then depending upon what hardware die implements, you should be able to claim reuse for the specific section. For example, here are some of the scenarios. If you implement a known answer test in the die, you should be able to reuse it. If you implement integrity mechanism, authentication mechanism, respective sections should be able to reuse the test evidence. Let's take the same example in a different context. So you still have that die which implements your AES, and it gets put into two different boundaries. One is the sub-chip boundary and one is the single chip module boundary. Let's say first case that the die only implements AES, then you can reuse the algorithm certificate. Let's say if it implements the algorithm as well as its self-test, then you can reuse the positive testing for that self-test as well as the negative testing that force the module into error state. Then if the die implements, let's say, key storage as well, you can cover the storage zeroization entry output. And finally, if it has also the service, that means even the die even provides you an interface where you can pass in your inputs, the inputs get verified by the hardware, and it also provides a data output or the status output depending on the service implemented. So you can see here, depending upon what is implemented in die, your reuse of items for the testing increases. And this is just a simple example with one algorithm. If you have more algorithms or more functionality, it should be able to have an impact to create more and more reuse that's possible. Then lastly, let's look at the ESV certificate reuse. The same section about the porting guidance, it says that the ESV retesting is required if entropy source is within the subchip boundary. It may not be required if it is outside the subchip boundary, depending upon if the entropy has changed or not when it got ported to the new IC or the new SoC. But in this case, what if your entropy source is entirely contained within one die? In that case, if you have a bare die that is getting transferred to the new package, but the die itself has not changed, which is confirmed through photomask ID, then you should be allowed to also claim the same ESV certificate reuse. And actually, 2 days back when Chris from ESV had his presentation, he did accept the fact, and he also had a slide specifically stating that they will allow reuse of the die ESV certificate as long as you have that information listed for a specific die. And we want to take this one step further. Similar to CAVP, we don't want to disclose the die information, so it should be allowed to have the IC package information and then let the mapping done through the lab and the vendor internally when sending the report to the CMVP. So we looked at what are the possible reuse for different cases. Now let's look at what are the requirements for the module validation. These are again the proposed requirements that we are think of. This will get evolved as we get more feedback, we get some guidance from CMVP, but this is what we have figured out, it's minimum that is required. So first thing is the vendor shall be able to give all the information to the lab, specifically what photomask ID maps to which different IC packages that contain the die where they want to claim the reuse. The first job that the lab has to do is identify what is the portion of the module that is implemented within your die, because then only they can identify what testing can be reused. Then as mentioned earlier, the hardware configuration does matter. So the lab also has to verify that the hardware configuration either remains unchanged or it is not affecting the functionality of the die. And then lastly, the both certificates for ESV and CAVP should be allowed to either be tested at the die level or at least the mapping has to be provided within the test report. One example could be there is AS215 that asks for every hardware module to list all of the components. It's kind of like a bill of materials. So there can be two cases where the vendor already knows that they have 3 different IC packages with the same die and they want to test all of 3. Then we can just test on one die and then have that mapping provided in that IC, in that specific test element by listing all of the details. When they say that the photomask ID for all 3 packages for that specific die is exactly same, then the reuse can already be claimed. And this can also be done during a revalidation where you want to add a new chip that is reusing the same die. You should not be required to do all of the testing again. So finally, this is the summary, which is, just going over the point, but because of short of time, I just want to stress on the last point here. So past few meetings, if you are attending the RFG working group, we have given through 2 or 3 rounds of the reuse of testing. We first focus on the RFG only on the algorithm certificate, and now it's back to the CAVP back to the CMVP to accept the traceability that we are talking about, where you can list the IC name and don't have to list the die. Once that gets approved by CMVP, our next step will be to have a second version of the RFG where we go more detail and not just algorithm, but we can have a functional test reuse depending upon different categories of the module and different scenarios of what's being implemented. So we'll still work on these things, and if you have any feedback, we'll be welcoming. Thank you.
It looks like we have questions, so let's just straight to questions.
Hi, thanks for your presentation. So I have some concerns, and I'm sorry if I'm misinterpreting things, but maybe you can help me understand this. So the whole point of doing like algorithms in HDL when you're making semiconductors is to decouple yourself from the technology nodes and the lithography. So you design your algorithms and then you use tools to synthesize it into hardware. So I don't understand the concept of requiring physical equivalency for HDL things. And then I can tell you right now that you're probably going to have a riot if you tell vendors, semiconductor manufacturers, that they need to use photomasks for their algorithms. And then thirdly, the idea that the ESV is equivalent by die is something that we've said for convenience because we needed to pick something. But I can make an argument, a strong, compelling argument that you have, let's say you have an entropy source that's on one product that's, let's say a one processor, and then you've got the same entropy source design on another processor. I can make an argument that those are more equivalent if they're in the same location of the wafer than 2 entropy sources that are from the same product that are on different locations of the wafer, because the electrical parameters vary across the wafer with any modern semiconductor process.
Right,
so
right.
I don't understand, it seems a little arbitrary.
Yeah.
And yeah.
Yeah, so I think the location that you mentioned, we will categorize that as part of configuration. So I'm not saying that one die from one chip to another chip, you have a direct equivalency, but you do need to look at some of the characteristics, but that again depends on what is being implemented. Then your question about the HDL, so even right now, even if you have the same HDL, when you are implementing it in two different packages, you cannot claim any equivalency. You have to test on each and every chipset or in each and every OE that you are implementing.
Why do you need to do that? What would be
Because
different?
any algorithm testing is not possible at a source code level. The HDL will still be considered an equivalent to a source code and not to the physical implementation. And that's a requirement from FIP side. It's always been there. Yeah.
Would you consider having a standard?
Okay.
Yeah. One last question. Would
Yeah.
you consider having a standard like either JTAG or I2C primitive that the vendors could have a register with hard-coded values so that CST labs could just scan that out and get the ID as opposed to relying on a vendor providing them with a photo mask? Because photo masks are really, it's going to make things really complicated and hard for the vendors.
Okay. Yeah, I think we'll take this feedback and discuss with you later. Thank you.
I want to thank Yann and Swapneela. Good presentation. Thank you. Presentation in this session, we have Renaudt Nunez from atsec, who will be talking about physical security of single chips. Thank you.
How does this work? Okay, so I just click. Cool. All right. How do I go back? Figured it out. Okay, so good morning, everyone. My name is Renaudt Nunez, and today I will be presenting on the physical security of single chips. So my presentation overview basically is what I want to do is go over some of the basics of physical security goals that are already defined within the FIPS 140 standard. I also want to reacquaint ourselves with the physical security requirements through the different generations of the FIPS 140-X standard. Then we will explore a little bit about the single chip packaging technologies that already exist. And then from my personal opinion will be to express some of the downsides that I consider with the current standard. And lastly, as I do this, I don't just want to make complaints, but rather provide some suggestions as to things that could be used in the future to help make this program a little bit better. So to start out with, just a quick run through what the physical security goes, and these come from the FIPS 140 standard. So a cryptographic module is supposed to be designed to employ physical security mechanisms in order to restrict the unauthorized physical access to the contents and to deter unauthorized use or unauthorized modification of the module. And then the second thing is that the entire contents of the module, which include all the hardware, all the firmware, and all the software, is supposed to be protected, right? The security mechanisms that are employed will largely depend on the type of embodiment that the module is. And then just for the sake of our discussion, I just want to describe what tamper evidence is. The tamper evidence is the visible signs that are left by an unauthorized access attempt, okay? And lastly, the last bullet is really just a statement that you will see through this presentation that I want to beat into everyone's head, is that because of its small size and its fabrication, a single chip has some inherent tamper-resistant properties already built in. So I don't know how well you can see this table, but this is basically the physical security requirements for single chips, and this is through the years of generations of the standard. So we start out with the FIPS 140-1, -2, and then go into the -3, and what will be the future, and I actually haven't updated this, but if I remember correctly, we're going to FIPS 140-4, and so that will be the replacement for the X. Now this table really describes the single chip requirements, what the physical security requirements are for single chips. And so starting at the lowest level, security level 1, really there isn't any physical security requirements other than the module is made using production grade equipment. For the security level 2, what the requirement adds is opaque tamper evident coatings on the chip or the enclosure. Then when you go up to level 3, it's asking for you to have a hard, opaque, tamper-evident coating or a strong, resistant, removal-resistant enclosure. And then for the last, the most highest level, what it's asking for is solvency characteristics. So making sure that the dissolving of the coating will have a high probability of damaging the module itself. And then for the security level 4, they also add the requirement of EFP and EFT. Now, this one is not specific for single chips. It's also applicable to all the other module embodiments, but I just want to put it in here for clarity. Now, one thing I want to just show you is if you look, I get to use this. So this next column over, you have the FIPS 140-3. Now, as you can see from most of the requirements, nothing has changed. The security level 1 and security level 2 both were the same. And for the security level 3, the only thing that was really changed is that they moved the requirement of having the EFP or EFT to the security level 3. And then for the security level 4, they removed the option of having EFT and required only EFP as a mechanism to validate that. That's really the only change. From the FDIS of the ISO standard, I haven't seen any changes in any of the security levels from the 140-3 to what will be the 140-4. And really one of the things that I want to point out to you, as I said at the beginning, is this line right here. The security level 1 and 2 requirements for single chips has not changed in 30 years. Okay, let's see. So, just for reference, this is 30 years ago. So in 30 years ago, the devices that existed was this Intel Pentium 75. 75 means 75 megahertz. It went into this Acorn RISC PC 600. Which also included a disk drive, and I believe that's a zip drive right next to it. And then the first flash drive is on the bottom. It's an M-disk chip that went onto a card that was then loaded onto a computer, and that was your first flash drive. So the tokens that you have now with your keychains, this is the father. So just so you're aware of where we came from and where the standard has been. Okay, so now let's take a little bit of a shift. And let's kind of describe some of the technology that exists out there. So what I wanted to do is, I can't go through an exhaustive list of all the different package types that exist, so I'll just give you kind of a summary of some of the ones that I've seen throughout the years that I've worked at atsec, and just kind of in general in the market, the things that exist, right? So they typically come in 3 different types, or at least the more common ones. We have our through-hole packages. So these are the ones that are like the DIP packages. This is a dual inline package. And these are meant to go inside of the PCB and usually soldered from the backside of it, and it holds it in place onto the PCB. You want to replace it, you desolder, you pull it out, put another chip in there. The next thing you have is the surface mount technology, and this one is pretty broad. It has a lot of different, thin quad flat pack. You have your BGAs, your LGAs, all the different types of devices, chips that go mounted onto the surface of the PCB, the motherboard itself. And they're typically either soldered down themselves as part of the reflow process or are socketed by using some form of tension. And then the last package I'll talk about is the smart cards. So these are really called the UICC, Universal Integrated Circuit Card. I missed the card in that, but that's what it stands for. And so these are typically the SIM cards that are found in your phones, used for some of your login cards that you use for the building access, etc. So within this technology, I just want to kind of share a little bit of what's already used, how does these manufacturers, and what do they already provide. Now, the key thing that I want to provide you with here is that these manufacturing processes are not intended to meet security. And that's ironic because what I'm asking for is to look at it from a security perspective. But the manufacturers do this to provide assurance that their devices will operate properly, right? And so as you see here in this example, this is a flip chip technology. So this is something that you see a lot of the times on single chips that are mostly from the 2000s, 90s, discrete component surface mount devices. And so the way this technology is manufactured is that you have this IC that is created on the wafer, and they put metal surfaces on the pads where it's going to actually make the connection with the larger PCB. And then, as you can see in that second picture, these little solder balls are added to that metallized pads, and then they're flipped over. So when they're flipped over, they're soldered onto the PCB that becomes this chip right here, and then they're filled in with this underfill here. So what you end up with is a chip that, when you look at it from the top of it, is not actually exposed to anything because you're looking at the butt, the upside down portion of it. The die itself is connected inside and the bottom, as you can see in these pads here. This black little line right here would be where it makes a connection to the PCB. And then each one of these balls are actually covered with an epoxy resin. And so you create this seal all the way around the die itself, and it protects all of the connections that make the direct path from the die to the PCB, and essentially leaves the only access to this device to be the very bottom of the chip, as it's intended, okay? So now we'll talk about, similarly, on a SIM card. On a SIM card, exactly the same way. What you see here in this blue piece here is not actually the encapsulation process. The process is actually on the chip itself, this gold piece that you see here in this picture. This resin is applied on that die as well, and it's upside down as well. So when you look at it, the interface that you're looking is the butt, the interfaces that you're intended to. You don't actually get to see the inside of it. It's covered with this epoxy that is further encapsulated in this plastic card. The wire bonds are protected using this encapsulation. And if you were to look at an X-ray picture of it, this is what you would see here. This is the die in the very middle with little traces that are forming out to the pin locations where from the outside axis you would touch. All right, and then the last one. Ooh. Okay, this one is going to be tricky. Do you know how to push the button in there? I have a video, and I don't know if I'm going to be able to show it. So this is in the meantime, I'll at least talk about it and then see what we can do. But this is also kind of as a third type, which is these dip packages. So here's a slight video that I'll just show you. It's kind of the decapsulation process that you would go through in order to reach to something of value. And so in this process here, they're using this middle device here that's called a laser machine, very smart name. So it's etching the chip itself so that you can get it exposed, and eventually you should be able to access what you see here in the picture down low. The individual pins are available to the die itself. Now, again, what I'm trying to illustrate here is the level of requirement that you would need to achieve in order to get anything of value to this chip. You would have to use this type of machine to even get to the die itself. Now, the second thing that I want to say is, even though, and I think you can stop the video now, otherwise it'll keep playing. So one of the things that I would say is that even if you were to access this using one of these laser machines, what is the value that you would see when the opacity is still provided from the level of a human eye can't actually see anything in here? Right? So if we were looking at an HSM and you opened up the cover, you would see some of the components that are there. And if you know some of the vulnerabilities from one of the PCI card or the network card, you can use that vulnerability to expose that HSM and make use of it to attack it. In these single chips, even if you were to decapsulate this top part of it, what you really just get access is a visual information on the chip die itself. And that within the scopes of level 1 and 2, that there isn't anything that we can possibly do there with this type of attack. Mm-hmm. Oh. Okay, so I've kind of described a little bit of the process of how these chips are manufactured, and I just wanted to kind of go back to what I consider the downsides of this physical security requirements as we have them now. So as I've explained, the single chips are manufactured such that the data, the control, the output pins are exposed by design, right? What you see is intended to be there, right? Everything else is protected by design. And the mechanisms that are used by the manufacturers are intended to protect it against the environment already. They're intending to protect that the connections are going to be strong enough that if I'm putting this into a device and it falls on the ground, the die won't break and that the pin connections won't rust with any kind of environment of being in the condensation or being out in your car. So those are already being provided by the manufacturer by design, not for the sake of protection of security, but because they want to protect the chip's value so that it lasts for a long time, okay? So, and then the hardness testing, it really does little to demonstrate the attacks against realistic attacks. And as you've probably heard a lot of the side channel discussions, and I'll show you a little picture of it a little later, those attacks are a lot easier to perform on this type of chips because it's just a matter of lifting a pin and putting in some resistor across that pin, the power pin, and then measuring that pin. All of that can be done without having to leave any kind of tamper evidence on the device itself. So the protection is really not equivalent to the requirement of having to perform a test for the sake of compliance, okay? I've said the tamper evidence is satisfied by design. I won't say that again, I guess I did. The physical security testing on the chips themselves are destructive. And one thing I'll show in the next slide is sometimes we're asked to redo some testing for the sake of moving to a new iteration of a standard, or if the project has moved from one chip to a new chip, but yet it's the firmware that's really loaded, and yet the device is still the same. We're still being asked to either demonstrate why it would be equivalent or to perform testing again. And so this chips are destructive. So the vendors, when you have a product, usually the initial design of the product, you don't have hundreds of samples. You have a very limited supply. So when you then have to provide samples to the lab so that they can do destructive testing on a chip that's very valuable because your entire design team is trying to figure out how to get these bugs out of there, then that makes it harder on the vendors to have to provide these samples for a testing that really doesn't give them a technical value behind it. And then just a personal note is just it's environmentally wasteful, really, in my opinion. I think that there's other things that we could be doing with our time that would be saving us a little bit of effort. So let's see. So this is just a little example. We received recently a guidance from the CMVP that was telling us that if we had received a FIPS 140-2 certificate on the module and we were moving to 140-3, that we would have to retest the devices. And even if the devices were exactly the same and the thing that you're changing or make maybe some firmware to meet some of the new requirements, you would still have to perform the testing. And again, this is not against the CMVP because the CMVP is doing the job that they need to do and the requirements are present for them, so they're enforcing the requirements that are there. So I understand that, but I think that going forward, what I want to do is to change that from the standard level so that we don't have to do this trickle-down effect anymore. The second thing is that they're asking for us to do a request for guidance from project to project, even 140-3. So if a product has been validated at 140-3 and you're moving into another newer update or something, even if it is a firmware, you have to provide some kind of equivalency argument that says that these are exactly the same. Again, as you can see, going back from 30 years, there's nothing that's changed in the physical security requirements, so the requirement of having to redo the testing, it adds a little bit of a kind of a quandary as to the value behind it. Okay, so instead of just saying, okay, well, everything is bad, what is it that we could be spending our time on? And so I was kind of trying to figure out, okay, well, what could we do with this time instead? How do we make it a little bit better? And so these are just some of the ideas that I came up with, and these aren't exhaustive, and it isn't anything definitive. I have a last slide that's going to be helpful, but the first thing is, let's remove this physical security testing requirement at security level 2 for single chips. Right? So there's a difference in that when I showed the slide that security level 2 for single chips requires hardness testing and it requires tamper evidence. On multi-chip and standalone devices that use labels, you have to perform that testing. I can understand leaving that type of requirement there, that the labels are indeed going to show demonstrative evidence of tampering. For single chips, though, I would say that for security level 2, make it like it is for the security level 1, a documentation exercise. As you saw from the table, it said that for the security level 1, there is no additional physical security requirements. Provide the evidence that this is actually made from production-grade equipment, then that would be sufficient to meet the security level 1. So my first suggestion is extend that to security level 2. Make it to where you provide evidence of what the manufacturing type is, what the package types are, and as long as it is of one of the standard technology types, then it should be equivalent, it should be accepted, and no need to go further from doing that. That eliminates the need of having to gather the resources, for the testers to spend the time breaking some devices, for writing a report, and it's going to save reviewers time in having to review a report that everyone knows is going to pass, right? So that's one thing, okay? So then what do we do with our time? We have now time to just sit around? No, we go around and look for other things to do. And so we have this protocols that are out there, and these protocols are important, and they're rooted in single chips, a lot of these, right? So we have here just a few examples. So one of them is having to do with secure boot. The other one is about SPDM and DICE, and I'll describe them a little bit just in general in a second. And then the last thing is, one of the things is to provide some collaboration with the people who are here today, and hopefully in the next ISO release that we can actually come back and say, hey, we talked about it and we met as a group and we formulated some ideas and we fed that back to the ISO community. They accepted it and then we changed it. That would be great. But I mean, that's just me personally, how I feel. Okay, so let's see. So a secure boot process. So this is one of the things that are used with single chips, right? So in a secure boot process, I'm not going to bore you guys. You guys already know this. You make this stuff. So it's very simple. There's a key that's stored within the single chip itself and is used as a root of trust, right? So this key is loaded by the manufacturers or made by the chip at the time of provisioning. And this key is intended to serve as a root of trust for the future generations of the firmware that's going to be loaded onto this chip. So one of the things that we could do is actually understand that secure boot process from a single chip. Create guidance here that gives vendors a method of, if you're going to be implementing the secure boot process, how do you make sure that your root keys are protected, that they're generated in the right way, and that they're used properly to derive the future keys? That's one area. Here's another one, also very similar. So if you're not familiar with DICE, this is the Device Identity Composition Engine. And so this is a protocol that's, a specification I would say, that's used to provide a hardware root of trust. Again, all of these protocols are very similar in fashion. So there's something here that I think we could work with. So in this DICE perspective, you also do the same thing. You have what's called a UDS, a unique device secret, that's either provisioned at the time of manufactured or is part of the device itself that uses some intrinsic noise to create this seed that then is used to generate the UDS, which is then subsequently used to generate layers and layers of keys that are used to verify the firmware that's loaded onto the device. Now the key itself, the very root of this is this UDS, which is found inside of the single chips. Okay, so that's another concept. And then the last one I'll talk about is the SPDM. So SPDM is very similar to the TLS protocol. So this is ideally how chip devices will talk to each other within a motherboard. So if two different chips that are on the same board want to communicate with each other and want to ensure that the chip is manufactured from a good source, and then they'll use this protocol to establish that communication. So in this established in SPDM, a lot of these keys are also stored inside of the chip. So you're starting to see that trend, right? A lot of these protocols use the same value, that there's something inside of a single chip that's stored and is used to provide the overall protection of the system. So I think that those things are something that we can actually start looking into as a community and providing more guidance on the single chip environment. So the last thing I want to say is just about the side channel attacks. There's been many different discussions about it throughout this, either this year, last year, or past 3-4 years that I've come to ICMC. So I won't repeat all this information, but just for a very basic, I just want to show the diagram that in most cases, whenever you're doing a differential analysis on the chips themselves, all you're really having to do is to lift a pin, a power pin of some sort, and provide that as a method to test. So you would put some resistor in between it, and you would measure it, collect the traces, and use that as a way to measure the side channel analysis. So this isn't very intrusive. I could pull the resistor out, do the measurements, put that pin right back, and from a tamper evidence perspective, it would pass, right? And so yet this provides a lot more security risk than me being able to scrape off a little bit of the top of the chip itself, okay? And so just for a little bit of a background, I will say one thing about TVLA. What is it? So this is a methodology that was initially, I think, presented by Cryptographic Research Institute, who is now Rambus, I believe. And they provided this at one of the NIST workshops, and it was a methodology to assess the leakage, right? And so right now in the ISO standard for security levels 1 and 2 for non-invasive channels, it says that you have to have methods documented. And maybe this is along the lines of what we do, could be to use this as a form to define what kind of things need to be in the code for security levels 1 and 2 in order to satisfy the TVLA for the non-invasive attacks. And so when I initially put together this abstract, I was hoping that I would come here, I would present this information, and then my Christmas list would be that I could have formed a physical security working group, and that we start doing this. But lucky for me, in one of the request for guidance working groups, there was a request that we start some kind of physical security working group to address some of the requests that were coming this way. And so we did. And so instead of asking for the community to join me in making a working group, I would invite you guys to join the working group. And so what I'm asking is to just, you can email me if you're interested in it, and that we have basically 5 years to go about trying to define something of value, find the right people. I know some of them are in the room right here to impress this on the ISO community first, so that way the ISO is the first one that gets rolled in, and then that way it trickles down into the FIP standard. And in the meantime, through this working group, my idea is that we could have some guidances that will help developers along the way before we get to that big change that I'm looking for. So I think that's it. Well, so these are FAQs. Really, I've already answered some of these. These are, can physical security test evidence from security level 2 be used at security level 3? And the answer, as we saw in that letter earlier, is no. You're supposed to perform retesting at this time, even when you're moving from a security level 2 to security level 3 with no physical security changes whatsoever. But now the question is, can you reuse it within a physical security, from a FIPS 140-3 report? And so now this is one thing that we're currently working on in the working group, is to create a first implementation guidance on how to reuse the test evidence from report to report, so that way you don't have to go retest and waste your time doing tests that we can already satisfy. So I think with that, that's it. I'll take any questions if there are any.
Do we have any questions on physical single chip security? No? Okay. Then I want to thank Renaudt again. One quick announcement.